Hello, statistics fans, and welcome to section 1.2, where we talk about random samples. If you recall from the last section, we learned that the purpose of inferential statistics is to learn about a population by studying a sample. And sampling is done all the time. The Bureau of Labor Statistics uses sampling to estimate the income of an average American or a typical American. Parts are sampled for quality control all over the world in manufacturing, and there's just a lot of times when we need to take a sample of the population. There are many reasons to sample. So it could be that to measure or observe each individual in the population could be time consuming, or maybe it could be too costly, or maybe even physically impossible. So imagine it is your first day on the job and you are working in a lab and they want you to determine the population of mosquitoes in Michigan by counting every single mosquito in Michigan. Where would you even start? There's too many to sample. There's mosquitoes dying and being born before you could possibly even get a tiny sample of the population. There's state lines that mosquitoes are crossing. It's not possible to actually count every mosquito in the state of Michigan. Also, sometimes sampling is destructive. So sometimes you have to take a stress test on concrete. So you take a sample of the concrete, you let it cure, and then perform some sort of stress test. Well, obviously that part of the concrete cannot be sold. It's been destroyed. Or even if you were a taste tester at Krispy Kreme, let's say you have this great job. You are at the end of the assembly line at Krispy Kreme, and your job is to sample every donut, take a bite out of every one, and if it passes the taste test, you put it on display. Probably not a great marketing plan. And sometimes it's just unnecessary to observe every individual in the population. The sample may give us all the information we need. Something very important about sampling is the sample should be unbiased. We say sample is biased if it systematically favors certain responses. We'll see that it's not all that easy to make this happen. I first found this out in second grade. We had a class election about who was going to be president of the United States. And I'm sure you guys remember this. 1976 election between Jerry Ford and Jimmy Carter. We took a vote in second grade. It wasn't even close. Jerry Ford won the election. And then later I remember my parents talking. They mentioned something about Jimmy Carter won the election. And I was like, oh, no, he didn't. I was there. It wasn't even close. It was like 21-4. How can you guys not know this? That's when I found out two things. Number one, second grade classroom elections don't count for the presidential election. And number two, my sample was extremely biased. Jerry Ford was from Grand Rapids, and we were a second grade classroom in Grand Rapids. And when you're in second grade, you probably just feel the way your parents do about a lot of things. So our sample was extremely biased. We've got another note here. The sample should be representative of the entire population. So it should be like a mini-me of the population where all the proportions are in place. And if this is done correctly, you don't need as many people as you might think to get good information from a sample. So for nationwide polls, typically only around 1,500 people are sampled. But you have to carefully choose these 1,500 people in order to get an accurate representation of the entire population. So let's look at some sampling techniques. The first one to look at is one you've probably heard of, a simple random sample. This is one that is done in such a manner that every sample of size n from the population has an equal chance of being selected. Now the part that may seem a little strange is the sample of size n, so n is some integer. So we have to choose the sample in a way that every sample of size 7, for instance, has an equal chance of being selected. And the fact that each individual has an equal chance of being selected for each individual is not enough to guarantee a simple random sample. So it's not just that any individual has an equal chance of being selected, it's that every sample of a given size must also have an equal chance of being selected. So to maybe clarify this a little bit, here is an example that's not a simple random sample. Now this example right here is from our book. This is let me write this one down. This is page 19, number 8. That's this one right here, page 19, problem number 8. And it says this: consider the students in your stats class as the population, and suppose they are seated in 4 rows of 10 students each. So let's just make these rows. Let's say we've got 4 rows here of 10 students. I've got 1, 2, 3, and let's say 4 rows here, 10 students each. So it says to select a sample, you toss a coin. If it comes up heads, you use the 20 students sitting in the first 2 rows. So if it's heads, we're going to use these 20 students. And if it's tails, we're going to use these 20 students. Okay, so we're just going to flip a coin. So question number 1 says, does every student have an equal chance of being selected for the sample? Well, think about it. Like this student who's sitting right here, that student's got a 50-50 chance, right, of being selected. Basically, you flip a coin. If it's a fair coin, there's a 50% chance of heads, 50% chance of tails. So this student has a 50% chance of being selected, which is the same as this student, that student, this student, right? Every student has a 50% chance of being selected with this. So the answer here is yes. Then part B says, is it possible to include a student sitting in row 3 with a student sitting in row 2 in your sample? Okay, so would I be able to include, let's say, this student in row 2 and this student in row 3? Would it be possible that with the way we're doing this, that both of these are selected? And obviously they can't be, right? Either this student if it's heads or this student if it's tails, but they're not both going to be selected. So think about what we're saying here. Okay, what about the population of these, or the probability of these 2 students being selected is 50%, right, for these 2? Because if the coin is flipped and if it comes up tails, these 2 are selected, 50% chance. But there's a 0% chance that these 2 will be selected, right? So this sample of a given size, this part falls when size 2, sample of size 2, this sample of size 2 has a 50% chance of being selected. This sample of size 2 has a 0% chance. Okay, so to answer the question, is it possible to include students sitting in row 3 with students sitting in row 2 in your sample? No. Whoops. Okay, let's try this again. No. So then it says, is your sample a simple random sample? No, it's not. Because these samples of size 2 don't have the same chance of being selected. So it's not a simple random sample. Then it says, describe a process you could use to get a simple random sample of size 20 from a class of size 40. So if you think about it, there's 40 students here, right? 10 in each row. We need to get a simple random sample of size 20. Can you think of a way to make this work? Now, you're probably thinking, many of you are probably thinking, well, what about if we just assign a number? There's 40 students, assign everybody a number, and then put like maybe 1 through 40 on a piece of paper, 40 little pieces of paper, 1 through 40, put them in a hat. Or, we could use a random number generator, which is more like what we would do. We'll show how to create a random number generator on the calculator, but basically just what we could do is assign every student a number 1 through 40 and then randomly choose 20 students. Another type of sampling is stratified sampling. This can be used when a population can be clearly divided into non-overlapping groups based on some characteristic. And each group would be called a stratum. So as an example, college students could be classified as freshmen, sophomores, juniors, or seniors, because these are all non-overlapping groups based on how many credits you've earned, or full-time, part-time. So pretty easy. There's a lot of groups, so a lot of ways you can do this with college students, male, female, etc. And then these groups, or strata, are then sampled using, let's see if you guys can figure this one out, SRS. Can you guess what I'm going to write there? You're probably thinking simple random samples, and you are correct. Often in proportion to their occurrence in the population. So what you do is you take your population, divide it into non-overlapping groups, and then from each of those groups you take a simple random sample. So it says here, often in proportion to their occurrence in the population, which is true. Our book doesn't mention this, but I'll talk about that a little bit. But first, let's look at this example. If you had a manufacturer of smart TVs, and they might want information about customer satisfaction for units produced during the previous year. So let's suppose they have 3 different models manufactured, and they want to take a sample from each of the 3 corresponding groups or strata. This results in information on all 3 models, ensure that no one model is over or underrepresented in the entire sample. So as an example, let's say this manufacturer sold thousands of smart TVs of these 3 different models, just thousands of them. And they want to conduct a survey. So if they just randomly send out maybe 200 surveys, by chance alone, maybe one of these models would get too many surveys, right? It could, maybe model 1 out of those 200 ends up getting 120 of those surveys just by random variation. So if you want to control for this, what you could do is just say, you know what, I'm going to send out 100 surveys to people who bought Model 1, 100 surveys to people who bought Model 2, and 100 surveys to people who bought Model 3. So you randomly choose these 100 people, these 100 people, and these 100 people, but you can control your survey results so that each model is represented. Also, maybe Model 3 was your best-selling product. Maybe you sold 5 times more Model 3 than Models 1 and 2. Well then, this is where this comes in. Sometimes what you'll do is you'll just send out 5 times as many surveys for Model 3 because you'll be sampling in proportion to how they were sold. So the note here mentions that selecting a simple random sample of size proportional to the stratum size is often called proportional sampling. And it's a lot like the House of Representatives in Congress. It's like proportional sampling because you get more representatives based on how large your state is. So, for instance, there are something like 7 states or so, states with a smaller population that get 1 rep, like Wyoming gets 1 rep. Where a large state like California, I think California used to get 53 reps. I think they're going to lose a rep, but still at 52 reps, it's a lot of reps because California has a large population. Now, Michigan had 15 reps, I believe, in the 80s, but we've been dropping ever since. So I think we have 13 reps now. So that would be like proportional sampling. But then if you have the Senate, then everybody's the same. You get 2 reps per state. So the main takeaway is with stratified sampling, you take your entire population, split it into non-overlapping groups, then you take a simple random sample of each group. Incidentally, some information about Congress. So there's 100 senators and 435 people in the House of Representatives. So a total of 535 people in Congress. Out of those 535, you might think, well, hopefully there's a lot of, let's say, scientists in that group because there's a lot of problems we need to solve. Scientists, pretty good at solving problems. So, how many scientists do you think are in that group of 535 members of Congress? Take a guess. If you're thinking 100, that might be nice, but no, there's around 6. Although I think we may have a couple more now, so maybe there's 8 scientists. What about engineers? Engineers are great at problem solving. There's a lot of problems to be solved. How many do we have? 5 engineers. Although again, I think that may have been a little proved in this last round, so we may have a couple more. The vast majority of people in the Senate and the House of Representatives are attorneys. So, okay, let's move on to systematic sampling. In this method, the elements of the population are arranged in some sort of sequential order. Okay, so systematic sampling you can sort of see coming when the method is described. So we put the elements of the population, we arrange them in some sort of sequential order, then we randomly select one element from the first K elements, which we'll talk about in a second here. Then every Kth element, starting with the first selected element, is included in the sample. So it's very systematic. You go right down the line, and I'll describe it with an example. And so for this example that I talked about, we don't have to know like why I'm doing this. We just have to understand when we see this happening that it's a systematic sample. So let's say we've got a file cabinet filled with 2,000 sales invoices, and let's say it's your first day on the job. You are the new person on the job. So just think from your past experience, when you're the brand new person on the job, do you get the great jobs or the not so great jobs? Probably the not so great jobs, right? So let's say you show up for work. You're like, I'm ready to work, boss. What do you need me to do? And your boss says, well, we've got this file cabinet downstairs with 2,000 sales invoices from the 80s, and we need to put those into electronic form so we can make sense of all that data. So your job is to go down there, look at those 2,000 sales invoices, and estimate the average sale. But of course, you don't want to go down there and look at all 2,000 invoices. So you want to take a sample and use that sample to approximate the average sale. So with systematic sampling, let's first start off with a question of how many will we choose to look at? And let's just say you think, well, maybe 100. Okay, now again, you don't have to know why I'm saying 100. We just have to understand this process when we see it. So we don't want to look at 2,000 invoices. So what we are going to do is look at 100 invoices. So we take the 2,000 total invoices. Did I just say, I think I said 100, right? We're going to look at 100. So we take 2,000, we divide it by 100. That gives us 20. So what we are going to do is we want to start with a random number between 1 and 20. And it doesn't matter what number you pick. So let's just say pick a random number. Let's say you pick 8. So let's say 8. Okay, so a random number is 8. So then what we do is we're going to use invoice number 8, 28, 48, 68, and so on. So what we did is we started at this 8. We take this 20, we just add to it. So we start at 8. So remember, these are in order. They're all in order. So we go with the 8th one, and then we select the 28th one, the 48th one, the 68th, the 88th, and we keep going. We keep counting by 20 until we get to the end of the list. When we're all done, we will have 100 of those invoices. Those are the 100 we are going to use for our sample. But we need to realize that there's a little note here. Okay, the note is this is not a simple random sample. So it is true that any of those invoices, each invoice has the same chance of being selected, right? Because we're basically starting, we pick a random number from 1 to 20. So if I would have chosen number 13, let's say. So if I would have chosen 13, I'd have 13, 33, 53, 73, etc. If I would have chosen number 2, then we'd have 2, 22, 42, 62. So because the way it's done, any one of these invoices has the same chance of being selected, but it's not a simple random sample because imagine this, okay? I'll say since invoice number 8, 17, 23, 29, 52, etc., has no chance of being selected in the process. This process would never select those invoices. So however this continues, these 100 invoices have zero chance of being selected because of the way we're doing it. It's very systematic. We're going to start at 8, go right down the list, 28, 48, 68, 88, 108. And you see it's very systematic. We have a starting point and we skip by the same amount right down the list every time. Very systematic. The name makes sense. It's a systematic sample. And this is popular among biologists, foresters, let's see, environmentalists, and marine scientists. And often what will be done is there'll be a grid system that's used. It'll be a numbered grid system that will then be used. Then systematic sampling will be used to collect samples. So usually about this time, students start wondering what do you have to know here? Okay, I'm never going to ask you to define something. Like, we don't have to know definitions of these things. Later on, we're going to do a problem out of the book, and you'll sort of see what we need to know. But we have to be able to read a process and then know what type of sampling there is. Okay, so once we go through these, there's a few more we'll look at, and we'll do one of the problems out of the book, so you'll get a feel for what we have to know. Okay, so next one we look at is a sampling technique called cluster sampling. And in this method, the whole population is first divided into these groups or these sections called clusters. And then we randomly select these clusters. So we're going to randomly select clusters, and then every member in the selected cluster is included in the survey. So sometimes this gets confused with what we looked at last time with stratified sampling, but they're different because thinking in cluster sampling, what we're going to do is we're going to first divide the entire population into these clusters. Now, a lot of times it'll be a large region, like say the state of Michigan. We divide into geographical sections. Maybe each county would be one of these clusters. So as this example, let's say we're going to do some survey for the state of Michigan. So we're going to consider each county a cluster. And there's, I think, 80 some counties in the state of Michigan. So each of those counties would be a cluster. So we're going to randomly select a handful of these clusters. So we randomly select a few counties, and then every member of the selected county would be included in the survey. All right, so whatever it is we're measuring, deer populations or some sort of voter registration question or whatever. What we do is every member in that selected county we'd want to count or interview or process somehow. So the note here, cluster sampling is often used by government agencies and in marketing research. So as an example, let's see how this works. Let's see you want to figure out how much TV does a 5th grade student in Michigan watch, and figure that out. Well, you know that if you're going to conduct a simple random sample, which would be nice, but to do that it would require the name of every 5th grade student at every school public, private, homeschooled, etc., from every corner of Michigan. So you would have to send a rep out or send an email or make a phone call to thousands of schools located all over the state of Michigan, and all the fifth grade elementary schools in the UP, public, private, get a hold of homeschool students. And when you just approach a school, a lot of schools will be very reluctant to give that information up. So a lot of times you're not going to be able to get the information from a school. So that would be just an enormous task. It'd be very time consuming and expensive. So instead, what if we consider each elementary school a cluster? We randomly select a few clusters. Then we interview every fifth grade student in the selected school. So instead of trying to get information from every fifth grade classroom in the state of Michigan, which would be thousands of them, it'd be much easier to get the names of all of those and then randomly select a few of those names, right? So maybe you would randomly select 20 fifth grade classrooms in the state of Michigan and then send your reps out to those 20 classrooms and hope that they would give you that information. But getting a hold of 20 schools, for instance, would be a lot better, a lot easier than trying to get a hold of every single school. One more thing I should probably mention, this section sometimes, believe it or not, some students think this section is not very exciting. I'm sure you disagree, but I just want to let you know some sections like this, there's just a lot of terms we need to know, and it's not the most exciting thing in the world. But don't think that statistics is this. It is not this. It is not me mentioning a bunch of terms and then we fill in the blanks about definitions and examples. That's not it. We have to have this basic terminology down so that we can do interesting things. So at the beginning of statistics, there's a little bit of things we just have to sort of grind through these terms so that they make sense. Again, I'm not going to ask you to define anything, but we have to have a working knowledge so that when we're talking or you're working on the homework, we know what we are talking about. Okay? So with that, two more. Multi-stage sampling. This refers to sampling plans where the sampling is carried out in stages using smaller and smaller sampling units at each stage. The final stage consisting of clusters. And really, that definition is a little stricter than usual. It's basically multi-stage sampling is how a lot of things are actually done, where there's different sampling methods all combined. So as an example of this, we've got the current population survey. This is a monthly survey of approximately 60,000 U.S. households conducted by the U.S. Census Bureau for the Bureau of Labor Statistics. And this is done every month. So there's a decent chance that many of you will be part of the survey at some time. And this is where, when you're watching the news and they'll say things like the latest employment figures are in, this is where they come from. They come from the current population survey. And if you want to go right to the source of the news and find out information that is put out, you can find it right from the U.S. Bureau of Labor Statistics website. So this is used, the current population survey is used to estimate the unemployment rate, income, poverty, health insurance coverage, etc. The last sampling technique we're going to look at, we saved the worst for last, is convenience sampling, which is just how it sounds. Very convenient, very easy. This is sampling using results or data that are conveniently and readily obtained. Often the data will be severely biased. Now sometimes this is the only thing you can do, but most of the time it's better to not use convenience sampling. So as an example, let's say the GRCC Financial Aid and Scholarship Department would like me to estimate the mean age of all GRCC students. And I'm like, well, it's going to take a lot of time to do this correctly. So instead, I just use the ages of students in this particular class as my sample. That sound like a good idea? Can you imagine any problems with this? So remember, if we want a sample to be a small representative of the entire population. So if I use any particular class, I have to think of some problems that are going to happen. Okay, day classes, the ages of day class students are typically a little bit younger than night class students. Also, School of Workforce Development, those students are typically a little older than the School of Arts and Sciences. And everyone in this class has something else in common. They needed statistics, so they wanted to take statistics. So it's probably not going to be a very good idea to do that. So I could absolutely do this. I could use the ages of the students in this particular class as my sample, and use that sample to make an estimate about the population mean age of all GRCC students, but it would not be a good idea. It would probably not be the best or the most accurate way to do this. But it would be convenient, right? So it's a convenient sample. So when you're working on the homework, if you read about a sampling technique, about somebody doing something, and you just feel like that's kind of sloppy, it doesn't look like your instinct will tell you this sort of sampling is probably not a good idea. A lot of times that'll be a convenient sample, and it'll look like this. It's just kind of like an easy way to sample, like too easy, not paying attention to a lot of details. That's convenient sampling. There's a phrase that we'll see that's a little bit misleading called sampling error, and this is just the difference between measurements from a sample and then the corresponding and measurements from the respective or corresponding population. It's just because of the fact that the sample does not perfectly represent the population. But the thing that's misleading is the name. So sampling errors are not mistakes. They're simply the consequences of using samples instead of population. So, for instance, let's say we've got, consider this the population. Just think of this as being a whole bunch of ages. And we want to know the mean age of GRCC students. And the mean age of a GRCC student. So we've got this population mean mu equals a question mark. So think of this just being a pile of thousands of numbers. Maybe there's 14,000 numbers here for each of the GRCC students, and we want to know, of those 14,000 numbers, what is the population mean, right? So this is the Greek letter mu for mean. What is this average age of a GRCC student? So what we do, let's say we don't have access to the entire population, we take a sample out of here. So we take a sample out of here. Let's say our sample size n is 100. And let's say the sample mean, let's say the mean of this sample is 27.2 years. Well, we don't expect this sample mean to be exactly the same as the population mean, right? This is a sample. Now, we hope that it will be close, but we don't expect it to be exactly the same. So in other words, if somebody else took another sample of size 100 from our population, we shouldn't be shocked if they don't get 27.2, right? They could definitely and probably would get something a little bit different. So the sampling error is just the difference between this number, 27.2, and this unknown number. Now the strange thing is when we get into chapter 7, we're going to learn how to put a bound on this error using what's called a confidence interval, which sounds like it couldn't be done because we actually don't know what this is, right? We don't know what this is, so how could we possibly put a bound and say, well, we're pretty sure this difference between x bar and mu is less than 3 or something like that. So we'll learn about that later, but sampling error is just the difference between this number, the actual true population mean, and our sample mean. So at this point, let's try a problem from the book so we can see what kind of things we need to know. So this one is a picture of page 21, number 20, and it's talking about sampling methods. So here's the kind of question we need to be able to do. So it says, Modern Managed Hospitals is a national for-profit chain of hospitals. Management wants to survey patients discharged this past year to obtain patient satisfaction profiles. They wish to use a sample of such patients. Several sampling techniques are described below. They want us to categorize each technique as simple random sample, stratified sample, systematic sample, cluster sample, or convenience sample. Okay, so this is what we need to be able to do, to read through these and tell which type of sampling technique was used. So let's just go through one at a time. So this one says, obtain a list of patients discharged from all of these facilities. Divide the patients according to the length of hospital stay. So if you can divide them up into these groups, 2 days or less, 3 to 7 days, 8 to 14 days, more than 14 days, and then draw simple random samples from each group. So what would be actually best? What would work best for you right now? So like if we were in a class, I would have you guys work on these, give you a few minutes and see what you come up with. You just go through A through E and look at what they're saying and look back at your notes, because the only way to do this, you have to think these through. If you just keep this on play and I just kind of ramble on through these where you're listening but you're not really thinking for yourself, you won't learn it as easily. And on the test, I won't be there to talk, so you're going to have to come up with these on your own. So the best thing to do, I read over part A, but read over all of them and see what you come up with. And then once you have an answer that you think is correct, press play again and see how it went. Okay, so hopefully you did that. If you didn't do that, you should do it. Press pause and then figure this out and then press play. So let's take a look. So we talked about this one already. So we broke these patients up into these groups, and then we drew a simple random sample from each group. So what does that sound like? It sounds like stratified sampling, right? Divide these up in non-overlapping groups, and we take a simple random sample from each group. Stratified sampling. Okay, part B, obtain list of patients discharged from all these facilities. Number these patients, then use a random number table to obtain the sample. So a couple things. So this book came out a long time ago, the same textbook we're using. And back then, it was more likely to use a random number table. It's not too likely to use one anymore, but we'll look at random number generators in a section coming up here pretty quickly. So what our book says random number table, you could use a table or random number generator. But the way this one is, we're going to number each of these patients and then use a random number table or generator to obtain a sample. So that is a simple random sample, because we numbered every patient and use a random number table or generator to obtain the sample. That is a simple random sample. Okay, part C, randomly select some of these facilities from each of 5 geographic regions. So you got these 5 regions. We're just going to randomly select some of these facilities and then include, here's the key word, all the patients on the discharge list of these selected hospitals. So we're going to randomly select some hospitals and then include all the patients on the discharge list. So what is that one? That's a cluster sample. We randomly select some of these hospitals and then we include all the patients of those selected hospitals. Okay, part D, at the beginning of the year, instruct each facility to survey every 500th patient. Every 500th patient gets surveyed. So it's like patient 500, 1,000, 1,500, 2,000. Doesn't that sound very systematic that we were doing this? That's a systematic sample. Okay, and then finally part E, instruct each facility to survey 10 discharged patients this week and send in the results. 10. 10. Any 10? These 10? Those 10? 10 randomly? See how it's like, it's just sort of sloppy. Yeah, survey 10 discharged patients. What, these 10? Yeah, those 10 will work. So it's just a convenience sample. It's very easy, not a lot of detail, just survey 10 of them and send it in. Okay, so that is a convenience sample. So at this point, let's take a look at number 6. This is on page 19, number 6. And this is where we switch over to maybe more of a critical thinking. So we've got an example here. It says a campus performance series features plays, music groups, dance troupes, and stand-up comedy. The committee responsible for selecting the performance groups includes 3 students chosen at random from a pool of volunteers. This year, the 30 volunteers came from a variety of majors. However, the 3 students for the committee were all music majors. Does this fact indicate there was bias in the selection process and that the selection process was not random? Explain. So why don't you press pause and just think about this a couple minutes and then come on back. So we just know, we don't have a lot of information. We only know that there were 30 volunteers. They came from a variety of majors, and the 3 students chosen for the committee were all music majors. And what the author wants us to start thinking about is how we should not jump to conclusions until we have enough information, we have some tools at our disposal to make use of that information. So for 30 volunteers, let's suppose, although they don't say this, I'm going to add information and then see if that changes anything. So let's say we're also given this information, which we're not, of course, but if we were. So if we knew that of these 30 volunteers, 20 of them were music majors, then maybe it wouldn't be so strange that of the 3 that were chosen, they were all music majors. But of course, we don't know this. So it could be that the case was something like this, or it could have been really just an unusual coincidence. Maybe there were only 5 music majors, but still, just by random chance, 3 of them, the 3 that were chosen, were all music majors. So we don't know this, but I just want to keep in mind there's a lot of things that could be happening that we don't know about. So we don't want to jump to conclusions and just assume that there must have been bias. Now, later on when we learn some statistical techniques, we'll be able to make a case. If we believe there's bias, we'll be able to make a case by using probabilities to weight to our claim. Let's look at another one of these. So this is real data. And this is from a while back, but from the National Weather Service. In previous 7 years, 376 of 439 people killed by lightning in the United States were men. So what that means is that 439 people were killed, 376 of them were men, 63 were women. So the ratio here is almost a 6-to-1 ratio. So it is a fact. During these 7 years, the fact is that men are 6 times more likely than women to be killed by lightning. Conclusion. What if this is my conclusion? I look at this fact and this is my conclusion. I say, well, it looks like lightning aims for men. Does that sound like a reasonable conclusion? Hopefully not, right? I mean, of course it's possible. There could be some unknown laws of physics, but it's far more likely that there's another reason for this. And in fact, the National Weather Service has a reason that they stated that the jobs and recreational habits of men make them more vulnerable to lightning. So line workers, for instance, typically are men. It's just, one of those fields where there's more men than women. Quite a bit more. So most line workers are males, and they're out there a lot of times during storms, working on the power lines. Recreational habits, golf, just seems to be maybe more men who are out golfing in the rain for whatever reason. So it just turns out that there are more men for the lightning to hit. So we don't want to see a fact and then jump to a conclusion, right? You want to be careful not to. That's what statistics will train you to, like, look for data first, and when you have data, then come to a conclusion. Which, as you may have noticed, is not really the normal thing to do. So we want that to be the thing that we do as statistics students. The last thing we have to be able to do in this section is to generate random numbers from our calculator. So I will show you how to generate random numbers on the TI-8384. But basically what we want to do is we look for the math menu on the TI-8384, and this is on the far left column. You press the math button. Then from there you scroll over to the probability drop-down menu and you choose number 5, which is random integer. Now from here, there's two different versions of the software. So I'll show you a video that has one version, but then I'm just going to mention the other version. When you press the math button on the far left, scroll over to probability, and then choose random integer with the open parenthesis. And the way it works is right here, you have your lower limit, your upper limit, and then how many. Now the how many part is optional, and the lower limit and the upper limit are inclusive, so it's including these. So, for instance, if I wanted to choose one number between 1 and 10, I would say random integer 1, 10. And I could leave this off, so I could just close the parenthesis, and it would give me one number between 1 and 10. And then if you wanted three numbers between 1 and 10, you would have random integer 1, 10, 3. So this is optional. If you leave it off, it just gives you 1. And then, as I mentioned, with the other version, when you choose random integer, this menu will come up here, and you would just type in, for instance, for us, we would say lower 1, upper 10, n would be how many. You could put 1, and then you hit paste. So actually, there's not a colon on paste. You just hit paste, and it'll put it on the screen, and then it will look just like this one. If I want to find a random number between 1 and 10, I go to the math button right there. You go math. Then I need to go over to probability. You can scroll right if you want, or it's quicker just to scroll to the left to probability, and then we want number 5, random integer. So I press number 5, and I have the input. The first input is the lower limit, then comma. The comma is right here, comma, upper limit 10. If I just want 1, you don't have to close the parentheses, but I'll close them. I just hit enter, and there it goes. And every time you hit enter, you get a different random integer. Now, if I wanted to get maybe, let's say 3 random integers, so then I would go math again, go over to probability, 5th one down. And just remember that some of you will have a newer software, and at this point it's going to have an intermediate menu, which will just ask you for lower, upper, and n. But let's say I wanted to go numbers between, I'll just do the same thing, 1 to 10, including 1 and 10, but this time I want 3 different numbers. Then you hit enter, and it will keep giving you random groups of 3 numbers between 1 and 10, including 1 and 10. Now, technically it's not a true random number generator because it doesn't have a clock to get a sample number from, like you could if you had a computer. This is technically called a pseudo random number generator, but it doesn't matter. It's going to give numbers that will come out in equal frequency, sort of like an electronic random number table. But so if we want to use a random number generator for this class, the way we do it, you go to math, go over to probability, and choose random integer, and then go from there. Sometimes students say, wait, when I did that, I got different numbers. Well, that's good, right? You're supposed to get different numbers, so you won't get the same numbers that I got. But let's say you wanted to choose your Mega Millions numbers with the TI-8384. I would not recommend doing anything with Mega Millions. We'll see in Chapter 4 that the odds of winning this are, well, I'll write it down now. spoil the suspense. 1 in 303 million. So that means don't play. But if you insist and you feel confident that your TI-8384 will give you the winning numbers, the way we could choose 5 numbers between 1 and 70, using our calculator, we just go random integer 1, comma 70, comma 5. You could fill in the blanks there. Basically, it's just to make sure it works. But then we would have to choose one number, the gold ball between 1 and 25. And so you could go 1, comma 25, put that number there. And to win the Mega Millions, you have to choose all of these and have them match the chosen numbers. And the odds of that happening are 1 in 303 million, which are not good odds. Now maybe you're thinking, no way, Kurt, my calculator would not lead me astray. It will pick the winner. If you think so, let me ask you a test question for your calculator. Ask your calculator this question. What is 10 to the 15th power plus 912 minus 10 to the 15 power? Okay, now we know what this should be, right? The answer should be 912. 10 to the 15th power, a big number, plus 912 minus 10 to the 15th power. These two cancel out, we just get 912. Ask your calculator that, see what it tells you. And if you have a TI-83 or 84, you're going to be disappointed because your calculator will tell you 0. It's because those calculators don't have computer algebra software. They use what's called the Cordic algorithm, which is like more of a brute force method. And this number is so large that it clogs up the memory so that it doesn't really have a good spot to put 912. So it doesn't really add it. So then when you subtract this off, it just says 0. So don't trust your calculator. The TI-83s and 84s are fantastic calculators. I really like them. They've been used, the TI series, for, gosh, probably around 30 years now. It was well written, and they're very user-friendly, but they're not perfect. So don't trust your calculator for everything. Okay, one last thing. You can use the random number table on page A9. If you really miss the 80s, you want to tight roll your jeans, wear high top Reeboks, and listen to cassette tapes, then you might like the random number table on page A9. We're not really going to do anything with it, but what we have to do in the bad old days, what we used to have to do before we had graphing calculators, we would just, from this table or a table like it, you would basically drop something on the table, wherever that thing lands, a paper clip, whatever is your starting point, and then you just go to the right, and those are your random numbers. Okay, so we're not going to do that. We'll use the calculator. But to use the calculator, how could we simulate the flip of a coin using the calculator? Using, in particular, the random integer command. Couldn't we just, for a flip of a coin, go like 1, 2, something like that? It would just count like 1s are heads, 2s are tails. You just keep doing this, you'll get a bunch of 1s and 2s, and you can count them for heads and tails. I'll tell you what we did in the bad old days when we had a table, we just do even and odd numbers. Same idea though. So we could do this. The roll of a die, you have to say something, because one time I was teaching this class and I talked about a die and I had a Dungeons and Dragons fan, and he would say to me, now Kurt, are we talking about a 6-sided die or maybe a 20-sided die or perhaps a 12-sided die? Okay, in this class it's always 6-sided die. That's what we're going to use, a 6-sided die every time. So for us, the roll, if we wanted to simulate the roll of a 6-sided die, we could do this. We could go random integer 1, 6, right? The bad old days with the table, we would just ignore 0s and 7s, 8s, and 9s. So it's much easier now. Roll of die, you can simulate that with a random number generator, just like this. And a little note here, our book will always ask us to use a random number table we can use our calculator instead. There's a few questions in the homework for this section, and they basically, the point is make sure you can generate a random number. That's it. That's all we really need to be able to do. Just use that command that we talked about, random integer, to generate a random number. Okay, now I have been thrilling you with this great lecture about section 1.2, and now it is your turn. So what you want to do is take a look at the section 1.2 homework, try them, and make a good attempt. It's really important. Homework is the most important thing you'll do in here to make sense of all these ideas. And if you have any questions, let me know.